Syzygy, episode 47, The Milky Way Explodes. And welcome back for another edition of the Syzygy podcast. My name's Chris Stewart. Opposite me here at the table, Emily Brunsden, as ever. Hey, Emily.
Hello, hello.
It's been a big week. It's been a big week for astronomy and cosmology. Nobel Prizes have been announced.
It's so exciting.
Yeah, the Physics Nobel Prize got announced earlier this week. Was it Monday or something? It's the first one of the sciences. No, medicine comes first, and then physics.
Tuesday was physics.
Tuesday was physics. And right up our alley, big time.
Astrophysics is winning the Nobel Prizes.
Huge, absolutely huge. Who got what?
So we got two Nobel Prizes, or the same Nobel Prizes jointly shared between two
Yeah, because they can
groups.
award it to up to three people, and they can kind of split that. It can be three people who all worked on the same thing and were equally responsible, at least as much as you can determine. Or it can be sort of in somewhat separate directions, and we give a bit for this person and a bit for this person. So I think they split it down the middle and said half of it goes to this person and the other half goes to these two people.
Yes.
For a different thing.
Yep.
Okay, so who's done what?
So the first one, the person on their own, if you like, was James Peebles, and he got the Nobel Prize for work he did on theoretical calculations of the universe, basically, looking at the history of the evolution of the universe. In particular, he was looking at the cosmic microwave background and the information that we can garner from this amazing observation.
Yeah, we talked a lot about that in the past. In fact, we talked about it in the last episode. I think we were talking about the cosmic microwave background and how it tells us about the energy density of the universe. Yeah, lots of very cool stuff.
And we did a whole episode on it with balloons.
We did
earlier
we
as
did.
well. So
telescopes on a balloon.
Go and have a look at those episodes if you want to know more about the CMB.
Mm-hmm.
And so that was really, really exciting. And that our understanding of the universe is just crazy advanced based on these observations and theories.
So that was worthy. Good.
Yes,
and the other half
very
went
good.
to?
The other one went to, I'm going to say Michael Mayer and Didier Queloz.
Mm-hmm.
And this is a really famous one. I mean, I'm so excited about this one because I talk about it all the time. This goes back to 1995.
Mm-hmm.
What happened in 1995 in astrophysics?
Well, given that you're very excited about it and given that it's very relevant to what we often talk about here on the podcast, I'm going to say it's exoplanets.
It's exoplanets, yeah.
Like the first one? Because if you're going to give a Nobel Prize, it's surely got to be for something very early on.
Yeah, it's the first one around an ordinary star.
Right.
Yeah.
Okay, so not the very first one, but the very first one that we would look at and go, that's a planetary system that we would recognize.
Exactly.
Right.
Yeah. So this is 51 Pag, B, one of the most famous exoplanets still to this day.
The rock star of exoplanets.
Yeah, our very, very first one. And it's one of these enormous hot Jupiters. And, it was a great story as to how these guys, everyone said you can't do it. You just can't. The planets are too small to have any kind of appreciable effect. You're just not going to see anything.
And they went, hold my beer. Look at this. Here we are. Well done all. Hasn't really done terribly much for the gender balance of the physics Nobel Prizes or the Nobel Prizes in general, to have another three guys up there. Not taking anything away from their work whatsoever, but it's pretty shocking.
It is, yeah. We do need to do better.
We do. Well, when they give us the Nobel Prize for Science Communication and it's an equal sharing between you and me, then that'll help to redress.
Yeah,
the balance
or you could just, give all your prize money to me, and then that would be even better.
We'll discuss. Yeah. We'll take that post-show, okay? So, look, that's the news of the week. That's very exciting. But some other news this week, which is really the meat of the show, is that apparently sometime in the past, the galaxy exploded. Which, news to me. I didn't know about that. Emily, what's going on? When did the galaxy explode? Why did the galaxy explode? Who found out? What?
Yes. So we need to use the word explode a little bit carefully here.
Okay. Should we reel that one back in?
So effectively what happened was the center of the galaxy had an enormous energetic flare event. This happened about 3.5 million years ago, and it left a tracer through some other parts of gas that we can see today, and we've been able to measure that, basically rewind the clock backwards and say, hold on a minute, the supermassive black hole at the center of our galaxy is a lot more interesting than maybe we once thought.
Which is an interesting statement in itself because, if you don't find a supermassive black hole interesting, I think there's something wrong with you. But anyway, parking that to the side for a moment, it's not terribly surprising that this did make some headlines, because it did.
Yes.
And all of those headlines were along the lines of, hey, guess what? our galaxy exploded a couple of million years ago, which is not that long ago in the grand scheme of things.
It's really
astronomically.
not. It's really not.
Very
That's why
recently.
this is exciting too.
It's, look, naively, and I do say naive things on this podcast from time to time. Naively, I would have thought, given that it was so recent cosmically, how is it that we didn't notice that? Maybe we can come to that a little bit later. First of all, who's done the work? Who are we applauding today?
Yeah, so this is work that's been led by Professor Joss Bland-Hawthorne from University of Sydney. And he's chairing up a project called Astro 3D. We're not going to talk about that acronym.
Yes. Look, well done on the research, Joss, but work harder on the acronym next time. That's all we're going to say.
That's all we're going to say.
Yeah.
So this is a project which has been looking at basically the Magellanic Stream in the galaxy. So this is a part of our galaxy which is it's not part of the ordinary spiral disk that we imagine when we think of our grand spiral Milky Way. It's actually a stream of material that goes, well, I guess up and down don't make a lot of sense. But
if you imagine your classic spiral galaxy is sort of flat and plate shaped, then you can think of it in terms of up and down as being sort of perpendicular to that. So is that what we're talking about?
So I guess it's
above and below that plate.
It's below, it's below the plate and kind of an arch. This Magellanic Stream. Yeah.
Okay.
So they were looking at that, and they were able to find traces basically in the stream that signify that we had this enormous flare explosion event 3.5 million years ago.
Very cool. So excellent work. How do we find our way into this one? Do we need to talk a little bit about the structure of the galaxy?
Yeah, let's start with that.
All right.
Because it's helpful to have a kind of imaginary galaxy in your mind when we're talking about where we're finding this information. So we've got a galaxy that's a beautiful grand spiral. We've got a bulge at the center of the galaxy, which is a bit more spherical. So it's kind of like a ball of more stars and gas close to the supermassive black hole. Now, I'm going to use units of light years. They're not going to sound like very large numbers of light years, but just keep in the back of your mind that a light year is a very, very, very large distance.
Yes. I mean, by definition, it's how far light can travel in a year, and light goes really, really fast.
Yes.
Okay.
So using light years, then we live something like 26,000 light years away from the center of the galaxy.
See, I'm going to disagree with you. I think that already starts sounding like a very long way. But anyway, all right, 26,000...
Yeah, if I put it in meters, though, then it might be a bit more.
26,000 light years from the center of the galaxy. And we're, about 2/3 the way out along a spiral arm? That's what Douglas Adams always used to say.
Yeah, about 2/3 the way, well, at least of the visible part of the galaxy.
Yeah.
Right, let's
that's a whole other question. Sure.
Yeah. So the whole disk, if you like, of the galaxy, if you went from kind of side to side, is something like 150 to 200,000 light years across.
Okay. So that gives us a sense of scale of the galaxy.
Yep.
What did you say? A couple of 100,000 light years across.
Yep.
Cool.
And so then the disk itself is quite thin. Well, it's literally called the thin disk.
Right. Well, that would be why it has that name then. Yes.
Yeah. So this the thin disk is only 2,000 light years thick.
So a couple of 100,000 wide, 2,000. Yeah. Okay. That's quite thin.
Yeah. I had a bit of fun with this a wee while ago. I was thinking about pancakes.
Yeah.
Because there's a lot of objects in the universe that kind of resemble pancakes. I think I was quite hungry at the time when I was doing this idea.
Analogies come to you as your brain is particularly switched on in that direction. So pancakes, good.
Yeah. So basically, with physics, when you collapse down anything that's spherical whilst it's rotating, then you end up with a disk.
Makes sense. You spin it around and the spinny type forces squash it down. Yep.
Yeah. So that's why we have disks, say, with the rings of Saturn. The solar system is a disk, effectively. Then you have galaxies, which are disks. So there's lots of disks, basically.
I mean, even the Earth is a bit squashed, isn't it? It's a squashed sphere, oblate spheroid.
So all of this angular momentum basically compresses things down to disks. And I was kind of thinking, I wonder what is like, if you scale things to the size of pancakes, which would make a delicious pancake out of these objects.
Okay.
It's too thick and, it gets a bit gooey and the batter isn't cooked in the middle. And too thin, then, it's not going to absorb all your butter and sauce.
I mean, are we talking crepey type pancakes or sort of your American big fluffy styly pancakes?
Well, that's what's interesting. You can to see what is what.
Okay.
Know? And it turns out that if you look at the galaxy and you imagine that scaled down to a pancake. Now, I'm going to be indulgent and say the pancake is the size of a dinner plate.
Okay.
Because I'm quite hungry.
Yeah.
If you do that, then your pancake is only about 2 millimeters thick.
Oh, that's very crepey.
It's very crepey.
Yeah. Yeah, that's your sort of very delicate, crepey, a little bit of lemon and sugar. Nom, nom, nom.
Yeah.
Yeah.
So that's a good thing to hold in your mind when you think about the galaxy.
And that is very thin.
It's very thin.
Ah, wow.
That's a coin, basically, like a 5p coin in the UK.
Oh, that is really surprising to me. If you'd asked me to draw the galaxy side on, I would have said it was a lot thicker than that. So there we are. The thin disk is aptly named. Well done.
So that's basically the structure. And now we have this Magellanic Stream.
Mm-hmm.
So we have these two sort of satellite dwarf galaxies to the Milky Way.
The Magellanic Clouds.
We have a few, but the two very famous ones, Magellanic Clouds.
Yeah, there are a bunch, aren't there?
Yeah.
Yeah, okay. But the Magellanic Clouds, there's two of them.
Yep. And you can see them in the night sky in the southern hemisphere. So they're two sort of smudgy things. My very first description of them from a professional astronomer was it looked like someone sneezed on the sky over there.
Nice. Okay. Yeah, but that works.
Yeah.
I have seen them as well, and that's about right.
Yeah. So the two clouds are called the Large Magellanic Cloud and the Small Magellanic Cloud.
Okay.
Not super creative, but however.
Descriptive, though.
Yeah. So LMC, SMC. So there's this ribbon. Now, there's a Magellanic Stream, which is basically this ribbon-like structure that kind of is like a big tail coming out from these galaxies.
Okay. And is this stars? Is it what is it?
It's mostly gas.
Okay.
So it's gas that's been stripped out of these galaxies by the gravitational interaction that they have with our enormous Milky Way.
Right.
Because these things are tiny in comparison to us.
And are these galaxies that we've sort of gobbled up or attracted to in orbit? Like, where have they come from?
So they've come from elsewhere. So they've come from elsewhere in the local group, basically, and we're just in the process of consuming them.
Right. Okay. And so the stream is a result of those galaxies interacting with our galaxy and our much, much bigger galaxy, what's sort of stripping them apart? That's the idea?
Yeah, basically. And what's quite interesting is last year, actually, there was some new research that came out about where did this gas come from? Did it come from the LMC or the SMC? And interestingly, most of it comes from the Small Magellanic Cloud.
Right. Okay. All right. So we have our LMC, our SMC, and this stream of stuff.
And so to put that in our scale of the Milky Way, the stream is about 200,000 light years away.
So that's all of the order of the actual size of the galaxy itself.
Yeah. So double, if you took a kind of a radius, it's double the radius, if you like, from the center, except it's on the bottom of the galaxy, so it's underneath the dinner plate.
Right, okay.
Yeah, so, I mean, it's a huge part of astronomy is looking at the galactic structure generally, and, of course, the Astro 3D project is interested in mapping out the three-dimensional structure of these things like these streams. There's lots of them, actually. It's really, really cool. So this structure actually happens to sort of pass, if you like, below the bottom of the supermassive black hole.
Right, okay.
So when we talk about things like these flares, we're calling them Seyfert flares because they're similar to what we observe in Seyfert galaxies, which is a whole different type of active galaxy. And these supermassive black holes, when they have an energetic process, like they consume a star or another piece of matter, there's this dipole emission that comes from that. So it means that instead of being emission that comes out through the disk or through the equator of the black hole, if you like, which is normally how the material falls in,
right,
then the material is spewed up in the north and south pole.
Right. So when you say dipole, it's being sort of spat out. If you imagine your pancake on your plate, it's getting spat out above and below.
Yes.
In these sort of huge, jets?
Yeah.
Right.
Yeah. So we have these huge jets. They're called ionization cones of energy coming out from the top and the bottom of the supermassive black hole. So they're not going into the disk, they're going perpendicular to that.
Okay.
This is interesting for an audio podcast to describe all this.
But it's all right. We've got our pancake as reference. Yeah. Reference pancake. Yep.
Yeah. So it's like your pancake kind of exploded a little bit when you put it into the pan up into your face.
Yeah, okay, sure. That works. Why not? All right, so we have, at the moment, just trying to pull a few things together here. We have our pancake, that's our galaxy. We have the Magellanic Stream, which is down below the plate, down underneath.
Yeah, although up and down is kind of arbitrary at this point.
At the moment.
But yeah.
We have a black hole, which is every once in a while gobbling up something and burping out these huge explosions of stuff above and below the plate, above and below the pancake.
Yeah. So I've also seen this called like a lighthouse beam is
Right.
another way to think about it. And it sort of ends up as a cone because you start off as a point source and it kind of spreads out the further away that you get from the black hole.
Sure.
Yeah, and so this sort of blast of ionizing radiation hit the Magellanic Stream, or part of it.
And I'm guessing that it had a bit of an effect.
Just a bit of an effect, yeah. So what we're talking about when we're talking about radiation is radiation interacts with matter, right? So this is going to be high energy radiation that changes the structure of matter that it interacts with. And so particularly what this research has been looking at is that this radiation ionized a lot of molecules that are in the gas in the Magellanic Stream. And this ionization requires quite a lot of energy. So this is how we can back calculate that energy.
I see. Okay, so you look at the effect of the energy of the radiation smacking into the matter and going, well, the only way that it could have done that, the only way that it could have given that signature of ionized matter is if it was this energetic. You work it backwards and go, wow, that's a lot of energy.
Exactly. So these are Hubble Space Telescope's observations in the ultraviolet part of the spectrum. And they're basically looking at how much ionized stuff is there compared to how much neutral stuff.
Sure. And that would give you a sense of just how big a burp the supermassive black hole did at the time.
Exactly.
Okay.
Yeah. So this is quite cool. And it's the first time that I've particularly seen this black hole being referred to as like a Seyfert, for example. So a Seyfert galaxy is a type of very, very active galaxy that we see out there in the universe. And they have these objects very, very deep in the core, these supermassive black holes that we call AGN.
Active galactic nuclei. I think we've talked about those in a very early episode of this show.
Yeah. So these are active black holes, basically, that have material going into them through conservation of energy and through the insane just physics that are going on in these supermassive black holes. They are spitting out this dipole energy.
Right.
And we can see that.
And so are all AGN galaxies Seyfert galaxies, or is it just a particular kind of, that's doing an interesting thing in this way, we'll call it a Seyfert? What's the overlap?
So a Seyfert galaxy is a type of AGN.
Right.
So there's other types as well, but all Seyferts have AGNs.
Right.
In them. Yep.
So in the Venn diagram of AGNs, Seyfert is one lobe.
Yeah.
If you like. Okay,
yeah.
Cool.
So Seyfert galaxies are grand spiral galaxies like our own. They sort of look like they should be a normal spiral galaxy like our own. The only difference is if you add up all the energy that's coming from the core of a Seyfert galaxy, in other wavelengths, it outshines basically the entire galaxy.
Oh, so they're really rather active.
So the core is brighter than the whole luminosity of the entire galaxy put together.
Wow. And when you consider that there are hundreds of billions of stars in your average spiral galaxy, that's really quite bright indeed.
Yes, yeah.
Right. So
yeah.
these are particularly active, is what you're saying.
Exactly, yeah. And it's not always clear to us, for example, how these things can change over long periods of time, because we are always looking at a snapshot of the universe, right? We can't just fast forward or rewind the universe by a few billion years to see how these galaxies have changed over time. So it's an open area of research as to basically, are Seyfert galaxies always Seyfert, or do they go through Seyfert phases, for example? And this research is starting to say, well, maybe the Milky Way had a Seyfert kind of phase.
Right, because as you said a minute ago, it's the first time you have noticed people talking about our galaxy, the Milky Way, as, well, maybe it's kind of a Seyfert galaxy. Well, surely it either is or it isn't, but maybe it goes through these phases. Here's some evidence that at least several million years in the past, it was doing something which was a very good impression of a Seyfert galaxy.
Exactly, yeah. And this is not the only piece of evidence. So I have to admit, this has been something that's kind of passed me by in astronomical research.
Right. Well, you can't keep up with everything, Emily. You're a busy person.
I am, but this has got me excited. So I did go and read quite a bit about these other observations. So coming back to the early 2000s, we had these two space telescopes called Rosat and Fermi.
Well, I remember them, yes.
Yeah, so they were looking at X-rays and gamma rays, and they found these big bubbles of X-rays and gamma rays that still exist above and below the supermassive black hole.
Right, in our galaxy.
Yeah. And you see the images of these bubbles, and it's very striking. They look like a big lobe of radiation.
Right. And X-rays are high energy.
Yes.
So anytime you see large amounts of X-ray energy coming from something in the sky, you know that there's something really quite serious happening there.
Exactly.
Yeah.
There's also been some studies looking at hydrogen and how some, in the Magellanic Stream again, a particular section of the Magellanic Stream has a lot of hydrogen emission coming from it.
Okay.
Which again implies that you had to have some energy input in order to get the hydrogen up to a higher energy level. So in this case, it's the H-alpha line or Balmer line of hydrogen. So you have to pump it up with energy somehow.
Right.
And then it emits that energy back to us.
So it's not surprising that there's hydrogen there, because there's hydrogen everywhere in the
hydrogen
universe.
everywhere.
The surprising thing is that we see it, right? That it's got to be energized. It's got to have some kind of energy input to be bumping all those atoms up to a higher energy level so that they can then jump down to a lower energy level and give off some light. We see that only when there's energy being thrown into that system.
Exactly.
Right.
Yeah. So this is quite cool. It's kind of like another piece in the puzzle about understanding the evolution history of our Milky Way.
But given that other evidence was there before, is this new research simply confirming something, or is it kind of putting all the pieces of the puzzle together and going, hang on, I think we know what's going on here?
Yeah, I mean, the authors are quite cagey, I think, about this. I mean, they're sort of saying that, yes, this is all consistent. But I think they're also a bit, when you're a scientist, you always have that kind of little moment of doubt as well. So they are appreciative of the fact that, yes, these observations are all self-consistent with one another, but there are more observations needed to fully understand the deep nature of this particular emission.
Right, so it's a puzzle which is gradually coming together, but this is not the final piece.
Exactly, yeah.
Okay.
And there's actually a lot more that we can learn about the evolutionary history of the Milky Way by continuing these kinds of observations. And we're so lucky to have facilities such as Gaia, for example, which is doing this 3D mapping of our galaxy.
Remind me about Gaia. We have talked about it before, but I've got a very short memory.
Yeah, so Gaia is an ESO project where we're looking at measuring the distances to billions of stars in our galaxy.
Yeah, which is a big effort.
It's a huge effort. And the data that are coming back from Gaia are extraordinary. There's an amazing picture, which we'll put in the show notes, which is Gaia's picture of the Milky Way. And it looks like a photograph, but it's not a photograph.
It's data saying there's a star here,
it's
there's a star
measurements
here, there's a star. Wow.
Of where all the stars are.
That is awesome, because you don't tend to think about that, do you? You know, we get so used to seeing these amazing images of the night sky, and you can see, for example, things like the Hubble Deep Field and so on. Here are all these galaxies and all these points on the image. That's a galaxy, and that's a galaxy, and that's a galaxy, and that twinkly one, that's a star. But those are images, and something like Gaia, which is actually measuring and mapping out where things are in our galaxy and getting that level of detail, that's a whole other way of looking at the universe and understanding it. And that's quite an incredible accomplishment.
It's
because
amazing.
Galaxies are very complex and structured things.
Yeah, I mean, just the pure ambition of Gaia to say we're going to measure more billions of stars in our own galaxy is fantastic. And then some of the results that I've seen coming from it, we had data released too from Gaia earlier this year. They're just outstanding. They really are. So,
okay, let's bring some of this together then. We have evidence of a couple of million years ago, some ginormous explosion from the supermassive black hole in the center of our galaxy, spitting stuff up and down from the plane of our pancakey Milky Way, which is exceptionally thin, interesting enough, and colliding with this Magellanic Stream of stuff, of gas. And we see that in a bunch of different ways. My question to you is, like, we talk about big explosions and how energetic things are. Just how energetic was this?
Yeah, so hugely energetic.
Yeah.
I mean, we can measure this. I did look and see that we had a measurement in ergs, which is an unusual measurement for energy. But however, I mean, just to give you the number, it's something like 10 to the 60.
Okay. At that point, it doesn't really matter what an erg is. It's a measure of energy. But when you got 10 to the 60 of anything, it could be the smallest amount of energy possible. 10 to the 60, 1 followed by 60 zeros, that's a lot of anything.
That's a very, very large lot of energy.
So you got to sit up and pay attention. That's a big explosion.
And so it's interesting to think, 3.5 million years ago. This is not very long ago.
It's not. I mean, that's like dinosaurs. We're talking tens of millions, hundreds of millions. This is in a time between us and dinosaurs.
Dinosaurs didn't exist 3.5 million years ago. Yeah, they were long gone.
They've been wiped out. So we're well and truly into the mammals. We're into the primates. Some of our, distant but not too distant ancestors roaming the planet.
Exactly.
What would they have seen?
Yeah, so early humanoids, they would have to be in the southern hemisphere to be able to see because this is coming from the center of the galaxy.
Yep.
The center of our galaxy in our night sky comes from the constellation of Sagittarius.
Sure.
In fact, that's why our Milky Way black hole is called Sagittarius A star.
Right.
Because when we found it, we weren't really sure what it was. But,
but it's in Sagittarius.
That thing in Sagittarius that's doing weird
Sagittarius A star is basically astronomy's way of saying it's there. We don't know what it is. Yeah. Okay, so in the southern hemisphere, so we've got, I don't know, perhaps a bunch of very early sort of pre-human primates hanging around in Africa. And then, like in Australia, there would have been massive wombatty things, diprotodons wandering around looking up at the sky as they're chewing.
Well, I think it's even later than that. We've got early humanoids that from there isn't a name that I can't remember off the top of my head, but it's to do with Australia.
Okay.
For these type of people, then they're really not primates. They are early humans.
Right.
They do have the characteristics of human beings that we have today.
All right. So let's take that as read, and any
amazing,
sort of early humanoid anthropologists listening to this and going, oh, seriously, guys, get your act together. Look, do write in and tell us what we should have said. Meanwhile, we're just going to assume that someone was standing there looking up.
Yep. And they would have seen basically this enormous bright jet coming from the center of the Milky Way, up and down, up and below, above and below the center of the Milky Way, and it would have been brighter than any star in the night sky.
So we would have seen that.
We would have seen
in the night sky.
Definitely.
Wow. That would have been interesting. That would have created a few myths.
Exactly.
I think.
Imagine how you would explain that.
Although I'm guessing that it didn't just sort of happen like that. Like it wouldn't have been over, or would it have been? Like how quickly do these things come and go?
That's a good question. Not instantaneously.
No.
But I don't think we have a very good idea of the timescale exactly of how long these things last. But it's not human lifetime kind of instantaneous.
But if you can at least think of it in this way, if you're seeing it stretching across the sky, it becoming a large scale structure, you're talking light years of distance to many light years of distance. Therefore, you're talking at least many years to grow to that size.
Yes. And honestly, you can imagine, because most cultures in the world have stories, have myths about the night sky, have tales that are culturally appropriate to them. Lots have stories about the Milky Way. I mean, even the name Milky Way comes from Greek, where we're talking about a ribbon of milk through the sky, which is moderately odd, but that's part of their cultural explanation for what they were seeing. And so if you had this enormous perpendicular jet up and below, imagine what stories you could that would come from that.
We are quite good at incorporating new things and changes and so on into updates in our mythology. So even something which sort of perhaps slowly appeared but developed over a longer period of time, that could have made its way into a mythology if there was someone around making mythology at the time. And
it would have had a meaning to somebody.
Isn't
definitely.
that really interesting? Okay. All right, so
cool.
that, I find that fascinating that we would have actually have seen that. Wow. Would it have had, I'm kind of thinking now the sorts of things that you said before about we, don't hope that there's a supernova anywhere near by anytime soon because it would just wipe us out. Would there have been any negative impacts? I mean, this is a very energetic thing, but it's a very long way away. Would it have been something that we would have had to have worried about if we had, humans and satellites and mobile phones and stuff around at the time?
This is, of course, the kind of calculation that we love to do.
Yes, of course.
What would be the worst possible case scenario?
Yep.
Okay. So this particular, the way that the dipole of the black hole works means that it's by nature pointing away from us, right?
Sure, okay.
But let's just pretend.
Okay.
And let's pretend it pointed directly towards us.
Sure. Let's assume that we are right in the path of this thing, that it tipped over, that the big black hole in the center of the galaxy tipped over and it spattered in our direction, what would happen?
Okay, so first of all, there's a lot of stuff between us and the center of the galaxy.
Yes, there is.
In fact, there's so much stuff that if you go and look at the constellation of Sagittarius and look towards the center of the Milky Way, it just looks like a big black smudge.
Yeah, I mean, that's the weird thing about the center of the galaxy is it's really big and really bright, and we have great difficulty actually seeing it.
Yes.
Yeah, because there's lots of stuff in the way.
There's lots of stars, but importantly, there's also lots of gas and dust. So those big black clouds that you see in the beautiful pictures of the Milky Way, they're clouds of dust that are in the way.
Okay.
So basically, all this stuff does, protect us from this energetic flare. Nonetheless, if we had this big burst come towards us, then a calculation suggests that it would have about the same amount of impact as a moderate solar flare.
Right. Okay. And a moderate solar flare can cause troubles here on Earth. It can cause some very nice, aurora colours in the sky up towards the poles. But it's not hugely troubling.
It's inconvenient, I think, is the biggest thing. So it means it could knock out lots of our satellites, for example, GPS, internet, all that kind of stuff. Inconvenient.
Yeah.
It's dangerous.
But not sort of life on Earth ending.
No. It's dangerous if you're an astronaut on the International Space Station because they don't have the protection from Earth's atmosphere.
Right, yeah, so that would have been a worry.
So, there are ways that we can manage those risks for astronauts. We do have plans if the, huge solar flare goes off to bring astronauts back down to Earth, for example. So, again, inconvenient, but we can probably cope.
Yeah. Yeah, so in the very, very unlikely event that the supermassive black hole suddenly changes its axis of rotation and points in our direction and burps again, then it's not going to be such a huge problem.
Yeah, the bottom line is we've got bigger issues to worry about.
Right. Well, it's always good to learn that even in a worst case scenario where it's sort of, it's a minor inconvenience rather than life-ending threat from the center of the galaxy. On the other hand, as you said, it's always nice to do those worst case scenario calculations. And there's something built into the human condition, I think, Emily, that says we really want to learn that it's going to be really, really bad if we know that it's unlikely to happen. I don't know. Are you okay with that calculation, or are you a bit disappointed?
No,
like I am?
I think there is a dark side to human nature that always wants to know the most catastrophic ways that the world can end.
That's like why we like disaster movies. It's the same thing. I'm just imagining now how Hollywood would take this one on. Who would star? Bruce Willis? I don't know, going up into space, putting up a big reflective sail to bounce the...
No, I think we'd still have to nuke the black hole. That's our response to everything, right?
Yeah. Oh, well. Listen, we need to find our way out of this particular one. If you are an anthropologist who wants to get in touch to tell us just how wrong we are in thinking about who would have been looking up at the night sky 3 million years ago, or if you've got any other comment or question you want to make, there are a bunch of ways that you can get in touch with us. Emily, how do people get in touch with us?
We are on Twitter.
We are.
At SyzygyPod, SYZYGY pod. And good news is we've got basically the same handle everywhere.
Yeah. Anything that you can go and do on the social medias. Well, not anything. There are a lot, actually, that we're probably not on. But if you want to try us out, we will be SyzygyPod.
We're not on any dating websites at the moment.
We? No, we're definitely not. Definitely not on the.
Don't
on any
try
of
and
those.
find us
No.
there.
But otherwise, look on Facebook and on Twitter and on Instagram. We have a website as well, syzygy.fm. Very exciting thing coming up later in November. We are getting together with a bunch of other podcasters, not as astronautical podcasts, but podcasts from all different kinds of parts of life, up in the center of the galaxy of podcasting, in the universe, center of the universe of podcasting, which is Thirsk in North Yorkshire. There is the world's first podcast social club, being run by the same people who put together the Deershed Festival, which is a great North of England festival. And we're taking part in that. We're going to be doing a live show on the evening of Friday, the 22nd of November. So if you want to come along, grab a ticket, go to podcastsocialclub.com, find yourself a ticket, and come along and join us for that live show. It's going to be great fun. Looking forward to that one. But otherwise, that's pretty much it for another week. We're going to have to wrap this up, and we'll catch up with you in a week's time.
See you later.
Catch you later. Bye. Brian Schmitz, one of his postdocs or grad students or something, the day before the Nobel Prizes were announced, said to him, like, I'm gonna prank you tonight. I'm gonna call you in the wee hours of the morning and pretend to be from Sweden. So just be ready for it. And so when Brian Schmidt got the call, he's like, yeah, whatever, seriously. No, this really is Sweden. Yeah. Of course it is. Come on, fess up. No, really, it's Sweden. Oh, sorry. Hang on. Let me get dressed. Yeah.
Apparently one of the ones from this year, they couldn't get him on the phone for like half a day because he just didn't answer his phone.
I mean, I guess I kind of feel like surely you'd know. Like, wouldn't you know? But the shortlist isn't public. Like, people just don't know that this is coming, which is kind of freaky.
Yeah, and one of the other guys said, I was expecting a call, but I was expecting a call from the outcome of a big grant that I put in.
Right.
So when they got the call, they were very excited. They thought they had this big grant.
Yeah, that's great and all, but I need to get off the phone now because I'm waiting for another phone call.